Hi, my name is WalmyCuelloJimenez and I will be presenting the review on environmental and operational conditions effects on land wave-based structural health monitoring systems, a collaboration study between Jiangsu University and Dalian University of Technology in China. Over the past few decades, structural health monitoring has certainly emerged as a multidisciplinary technology with applications in multiple industries. The great number of breakthroughs in this area have contributed to reduce maintenance costs, increase productive life of the structures, and most importantly, improve safety. Several techniques have been researched for detecting damage on structural health monitoring applications. However, land waves have been considered suitable for these applications as a result of their ability to propagate over large distances, their ability to transmit through several structural features, and lastly, the small number of sensors required to be integrated into complex structures. Land waves are ultrasonic guided waves that propagate inside thin wall plates and shallow shells. They are present in two wave mode, symmetric and antisymmetric, which propagate independently from each other. Ultimately, the characterization of these waves is based on a group velocity versus frequency. When these waves are incident on damage, scattering takes place in all directions. Such a scatter is then used to investigate damage. However, an inherent issue with the use of land wave for structural monitoring consists of the complexity of the measured signals. In most cases, multiple modes as well as many reflections are present. Moreover, it is difficult to identify each feature in a given time trace, and to interpret each scatter due to the complexity of the wave signals. A manner to simplify damage-based scatter evaluation is to compare the signal captured during the operational life of the structure, known as the current signal, with the signal captured when the structure is known to be undamaged, known as the baseline signal, as seen in the graph. The simplest way to assess damage is to subtract the two signals, then leaving damage as the residual scatter. However, only when current and the baseline signals are taken at the same environmental and operational conditions, or EOCs. Analysis of the residual scatter, meaning evaluation of time of flight, amplitude, energy, etc., can then be used to characterize damage. A major constraint of this methodology comprises the influence of EOCs on the residual scatter after the signal subtraction takes place, mainly because the EOCs are likely to change the signal properties such as phase and amplitude, which then leads to changes in signal shape. Thereby, simply subtraction of the current from the baseline signal will most likely result in false scatters, and if used for structural health monitoring applications, it will result in false damage detection. Consequently, the focus of this review consists of investigating the effect of EOCs on land wave propagation along with compensation strategies thereof. A typical experimental setup consists of a metallic plate, at least two PCT sensors, a power amplifier, an oscilloscope, and a computer. The plate is placed in an environmental chamber to evaluate the effect of the different environmental and operational conditions on the wave parameters. A vibration plate capable of tailoring a wide range of frequencies is introduced for vibration evaluation, and a low or hydraulic load frame is employed for load evaluation. Temperature is perhaps the most critical environmental condition that influences land wave propagation and hence limiting their use for structural health monitoring applications. Initial study evaluated land wave at -40 and 60 Celsius at different frequencies. At 200 kHz, wave at 60 Celsius present larger time of flight and amplitude if compared to those at -40 Celsius. However, with increasing frequency to 350 kHz, the opposite behavior in terms of amplitude is attained. Thus, the wave response to temperature variation is not linearly related, and in fact, many mechanisms are known to induce changes in land wave signals as a result of temperature variation. Among those, material stiffness, elastic and shear moduli decreases with increasing temperature, hence the wave speed decrease, meaning signals at higher temperatures are expected to arrive later than those propagated at lower temperatures. Second, distance between sensors vary due to the expansion and contractions with changing temperatures, hence changing the wave speed. Third, the sensor properties such as piezoelectric coefficient and dielectric permittivity of both actuator and sensor are vary with changes in temperature resulting in amplitude changes. And lastly, the sensor specimen bond or the shear modulus variation of the adhesive layer as a result of temperature changes can be the most influential parameter in sensor signal when compared to other mechanical properties. In order to allow for optimum damage detection, multiple temperature compensation techniques are presented. First, data-driven techniques are comprised by optimal baseline subtraction, consists of collecting multiple baseline signals at various temperatures, then identifying the closer baseline at the temperature nearest to the current signal. Main disadvantage here is the large number of baseline required, and the advantage is the sensitivity attained. Second, the model-driven techniques, which consists of baseline signal stretch, requires a single baseline where the current signal is stretched or compressed to match the universal signal. The disadvantage here is that it depends on the structural complexity and the purity of the mode, and the advantage is the rapid computational time. Third, data fusion, which is a combination of OBS and BSS, requires multiple signals. Functionality consists of identifying the closest matching baseline and then further improving that by employing BSS. Four key disadvantages. Baseline reduction is limited by the BSS without the loss of sensitivity. Then the inability to place a full structure into the environmental chamber. Third, the assumption that the structure is healthy at the time the baseline is taken. And lastly, the structure can undergo changes that are not related to damage over time. The advantage here is the reduced number of baselines. Finally, co-integration, which is a property of non-stationary time series, where the augmented Dickey-Fuller test is used to find the degree of the non-stationary and also to detect damage. Stationary combinations are related to the environmental and operational conditions. When those are removed, the residual combinations are basically which contain the damage information. Main limitation here is that the ADF test parameters such as lag length have to be properly selected since it varies with damage type and severity, and if not selected properly, incorrect damage detection can be attained. The advantage is the successful removal of temperature effects, and finally the detection of damage with different severities. Here we see the effect of compensating lamp wave scatter for temperatures. In the results depicted herein, the black circle represents the damage location. When signals are not compensated, results indicate inaccurate damage identification. However, when optimal compensation is performed, the actual location of the damage is identified precisely. The other environmental condition investigated is moisture, which affects any property of composite that is dominated by the matrix. For example, the flexural module of glass fiber reinforced plastic composite decreases by hydroaging. Generally, moisture changes the dimensional and mechanical properties of composite material, hence affecting the wave propagation. On the other hand, the flexural strength of composite material is a fiber-dominated property, which reduces if the fiber is affected by moisture. This is mainly because the water can extract ions from the fiber and hence alter or modify the structure. Typically, the time of flight or wave velocity and amplitude are affected by moisture. Velocity reduces with increasing moisture content as illustrated in the chart. As a result, the typical baseline subtraction will result in false positives. Therefore, it is necessary to develop moisture effect compensation techniques. However, it should be noted that the effect of moisture on metallic structure is less critical than composite materials, because in metallic structures only sensor and the adhesive are affected by moisture, and ultimately this can be addressed by optimal selection of both sensors and the adhesive. The figure depicts the contrasts of signal measured in static conditions and under vibration are 10 kHz. Results indicated that the received time domain wave signals in vibrating structure will be deviated. This is due to external vibrations which generate flexural wave in addition to the lamp wave generated by the actuator. However, no changes on shape, phase, etc. was attained. Since the time of flight is a critical parameter for lamp wave-based structural monitoring applications, the effect of vibration of time of flight is also investigated. To achieve this, two specimens or aluminum plates with different dimensions and different boundary conditions were employed. It can be observed that for both specimens, the time of flight only fluctuates slightly as the vibration frequency changes, which could be attributed to measuring errors. Therefore, the time of flight were not affected by the external vibrations at the frequency study. Interestingly, frequencies evaluated cover most the dominant frequency ranges in practical operation ranges. Thus, this study indicates that structural monitoring algorithms developed based on time of flight are still effective even if the structures are subjected to vibrations. As a result, amplitude normalization of the baseline and current signal will eliminate the vibration-induced deviation. Then, since vibration doesn't change the phase and amplitude of the current signal, subtraction of baseline from the current signal will result in no false positive. This graph illustrates the scatter first arrivals for two paths at different directions, vertical and horizontal, under different loads. It is clear from the figure that the primary effect of a change in applied load on the collected lamp wave signal is a time shift or change in phase, followed by amplitude. However, the magnitude of the time shift for two paths are different. In fact, applied load changes affect propagation of lamp wave in homogeneous and isotropic materials by changing the dimensions and the wave speed of the target structure. Dimensions are changed as per the strain tensor, and wave speed change because of the acoustoelastic effect. Therefore, applied loads change in an initially isotropic medium into a slightly anisotropic one. Hence, the magnitude of the time shift due to varying applied loads depends on the propagation angle. Another evaluation consisted of application of uniaxial loading. Results indicate that the amplitudes of the scatter signal increase with increasing load. Furthermore, it can be noted that wave shape does not change significantly. Compensation strategy consists of using a model to relate the change in signal amplitude to that of the material properties. Researchers encountered that the features obtained from this relationship remain equal irrespective of load and geometry, making the methodology suitable for optimal load compensation. Figure depicts collected signal from two sensors with different adhesive thicknesses, 10 and 40 microns, at 50 kHz and at 500 kHz excitation frequencies. Results indicate that at a lower frequency, around 50 kHz, the signal with thin adhesive layer is stronger than for those with thicker layers. But at higher frequency, around 500 kHz, the amplitude of the signal with thin adhesive layer is smaller for those with thicker layer. It could be associated with the fact that the resonant phenomenon of the sensor is less constrained with a thicker and softer adhesive layer, so more energy might be generated by the actuator. Bonding defects may occur over time during the operational life of the structure, compromising the performance and reliability of the lamp wave-based structural monitoring system. Consequently, researchers compare the lamp wave propagation in path with equal distance through the same material, but from transducers with healthy and defective bonding, as shown in the schematic. Results indicate that the effect of bond defects on lamp wave propagation are remarkable, modifying the phase, amplitude, and shape of the propagation lamp wave, as shown in the chart. Moreover, these defects increase with the size of the actuator. Three key mechanisms are proposed for compensation purposes: finite element methodology that simulates the effect of bonding area and Jones modulus on phase and amplitude of the wave signal. Second, the frequency response features of the surface strain. And lastly, the ability to remove or repair the adhesive once its performance is compromised. As conclusion, in temperatures, the relationship with lamp wave response is not linear. For mechanisms induce changes in a scatter signal, we have the velocity decreases with increasing temperature, the time of flight changes with plate deformation, and as a result, in increase in temperature. The sensor properties such as piezoelectric coefficient and dielectric permittivity change with temperature, and in turn signal amplitude changes as well. And then the sensor and plate bond properties such as shear modulus and thicknesses vary with temperature. In terms of the compensation methodology, they consisted of OBS, BSS, data fusion, and co-integration. In terms of moisture, it generally affects properties dominated by the matrix in composite materials. Moisture absorption leads to signal amplitude reduction. It causes a relatively small reduction in wave velocity, and there's no major compensation methodologies reported. In terms of vibration, the amplitude time of flight do not vary with vibration, only the signals will be deviated. Compensation consists of amplitude normalization of the baseline and the current signal. In terms of load, the phase changes with load. Loads change an initial isotropic medium into a slightly anisotropic one. The magnitude and direction of the phase change depend on the propagation angle, and the compensation technique consists of numerical methods. In terms of adhesive, amplitude reduces with a decrease in shear modulus and increase in thickness. The resonant phenomenon must be considered since it's less constrained with softer and thicker layers. Bond defects change the phase, amplitude, and shape of the propagated wave, and the compensation technique involves FEM. Thank you.